Today is May 15th, and today we're going to study vectors, a quantity represented by an arrow with both direction and magnitude. Okay, but all kidding aside, I kind of cracked myself up there. You guys are probably rolling your eyes at me right now. You got to watch that video though on vectors. Okay, but seriously, we're going to study vectors today, okay? And quantities that we measure that have magnitude but they don't have direction are called scalars. Okay, so there's vectors and there's scalars. So like your age doesn't have direction, so that would be a scalar. Okay, something that doesn't need the direction you're going. Okay, all right. So a lot of things in physics require vectors like force and displacement or velocity and even acceleration, because you have positive acceleration and negative acceleration, so you have direction. Okay. So these are all they're represented by, they're called directed line segments. Okay, and those directed line segments are called vectors. All right. So a vector is in standard position if the initial point is at the origin. So like this right here. Okay, if the initial point right here, right there, is at 0, 0, we say it's in standard position. Okay, and then what we can do is we give the component form of the vector. Okay, and a lot of times this is really hard to write. Okay, it's bold. Okay, so this, we use boldface print to represent a vector, and then sometimes we do arrows too. And there's a lot of different notation for this. Okay, so let's say this point at the end of this directed line segment, right? Let's say it has coordinates something like this: 5, 6. Okay, and let's call this one A and this one B. Okay, so 0, 0 like this, and these aren't parentheses and they're not brackets. Okay, these are angled parentheses, I guess. I don't know what to call them. There, it's just that tells you, that symbol right there is telling you it's a vector. Okay, not the coordinates. Okay, so we call this the 0 vector, and it doesn't have direction. Okay, so we're like right here, and you can't tell the direction. If you put a point anywhere else, you can tell. Okay, so we would call this specific one, the way we would label this is we could label it U. Okay, we could also label it AB, and the initial point is A, so we start there and we draw an arrow going across like this. Okay, it's kind of like a ray in geometry. And then we can also name it this way, so it's going to be these like angled parentheses, I guess. Okay, and 5 comma 6, and then angled parentheses. And these are things that we can, these are going to be things that we can add, subtract, multiply, divide, all that kind of stuff. All right, so really we're not going to do calculus today. Okay, I'm just giving you the background for vectors. And you guys did vectors with Mr. Jet at the very beginning of physics. Okay, because you have to learn about vectors in that class. Okay, all right, so let's go to the next next page. Okay, so a lot of the stuff is going to be definitions. Okay, so if an arrow has initial point at x1, initial point at x1 comma y1, and that would be like r right here, or the 0, 0 right here. Okay, and terminal point x2 y2, that'd be like this point right here. It represents the vector. Okay, x2 minus x1, and that, it's like the change in x. Okay, this is the change in x, this is the change in y. Okay, so looking at this vector right here, right, its component form would look like this. Okay, we would write r s with an arrow starting at r going to s. Okay, and we would say this is equivalent to the vector, and we would do -2 minus -6. So -2 minus -6, comma, and then we would do 7 minus 2. Okay, so it's the head minus the tail, and this is called the head where the arrow is, and this is the tail where it starts. Okay, head minus tail rule. Okay, so we get this, right? And then that would become, when we do this, when we do the arithmetic in here, okay, this would become the vector -2 minus -6. Well, that'd be -2 plus 6, which would be 4, and 7 minus 2, which is 5. Okay, and if this is RS, and let's call this point right here, let's call this AB. Okay, AB would also have in component form would be 4, 5, okay? So because it would be 4 minus 0 and 5 minus 0, okay? So what this means is that AB, the vector AB, is equivalent to the vector RS because they both in component form become the vector 4 comma 5, okay? So we would say that these are equivalent vectors. Vectors. I just like saying the word. All right. Okay, hopefully that kind of makes sense. Okay, so all you have to do is subtract the components. Okay, and you have to do the head minus the tail. Okay, so you have to do the one that has the arrow because that's the direction it's going to go. Okay. All right. So that's kind of how we label them. Okay. Now we want to talk about the size of them. Okay. So the magnitude or the absolute value of a vector, okay, is the non-negative real number where we do this. Now really it's just the length of this. I want you to understand that. It's just the length, okay? Because this, if you go to the component form like this, okay, this is in standard position. This horizontal piece would be 4, so we're squaring it, right? And that's a leg of a right triangle. And this is 5, that's the vertical leg of a right triangle, right? So really, we're just finding the hypotenuse. That's all this is. Really, all this is Pythagorean theorem, okay? So if we want to do this one, right? If we want to find the magnitude of it, okay, we would take the absolute value of the vector 4 comma 5 like that, okay? And this is equivalent to the square root of 4 squared plus 5 squared, okay? And that would be the square root of 16 plus 25, and that would equal the square root of 41, okay? And that, okay, so that is the magnitude, the size of it, okay? It doesn't give you the direction. It's just the size of it, okay? So we're going to use an angle to also come up with the direction of it, okay? All right? A lot of times they're 180 degrees. Like a lot of times in physics, okay, you are going right and left. And so right would be positive and left would be negative, okay? All right? Okay, so let's talk about this next thing, the direction angle of a vector. Okay, so I want to talk about the direction angle of a vector, okay? And I apologize. I'm just going to be reading a lot of this, okay? Because it's just a lot of information to take in, all right? The direction angle of a non-zero vector v. Okay, so non-zero, so it's not 0, 0, right? It has to have some length to it. It has to have some magnitude to it, okay? Is the smallest non-negative angle, so it can't be negative, okay? Formed with the positive x-axis as the initial ray and the standard representation of V as the terminal ray. Okay, so what the heck does that mean, right? Okay, so if you look at this, I'm going to show 4 different representations, okay? All right, so here's one of them, okay? We could have it land right here, okay? And that would be non-negative, right? But the angle would be 0, okay? So the initial side right here on the positive x-axis, okay? And the terminal side also lands right here, okay? This is a lot like trigonometry, okay? Okay, so right here, that would be angle 0, okay? And it's non-negative, okay? And this would be vector V, okay? We could also, some other situations that could happen is you could land in the first quadrant, right? And this would be the vector V that I'm talking about. And this would be the angle right here, okay? And it would be angle theta, okay? And it has to be the smallest, so we can't go around twice, okay? Or once, more than once, okay? So all of these angles are between 0 degrees and 360 degrees. And vectors we do in degrees, not radians, okay? So another situation that could happen is we could land in the second quadrant, right? And we could land on the positive y-axis too, okay? That would just be a 90-degree angle, okay? And so we could have an angle theta here, okay? And then we could also have, and this would be vector V, I should say that, okay? We could land in the third quadrant. This would be vector V, and then the angle that we rotate, theta, would be this one, right? Okay? And then one more, we could land in the fourth quadrant. And if we land in the fourth quadrant, okay, so it has to be a positive angle. So we can't go this way, right? That's the whole big deal of it. Okay, you can't rotate this way with a negative angle. You have to rotate with a positive angle. So it's going to be counterclockwise from the positive x-axis, right, to this terminal ray. Okay, so it's going to look like this. Okay, and that would be my angle theta. I should have said over here, this is angle theta, and this is my vector v. Okay, so that's what it's going to look like. Okay, now what we're going to have to do is we're going to have to realize what quadrant the vector landed in. Okay, and what we're really going to get is the reference angle. Okay, so right here, angle theta and the reference angle are the same, right? The angle of like a triangle, like we did. Okay, all right, over here, we're going to find this angle. And what we'll know to do once we find that angle, okay, and we know the vector lands in the second quadrant, all we have to do is take 180 degrees minus whatever that angle is, and that would give us the direction angle, okay? Over here, if it was in the third quadrant, which means your vectors, both coordinates right here would both be negative, right? Okay, so we can tell where it's located based on what the sign of these are, okay? All right, so you can think of these as being like the endpoints, okay? All right, so right here, this would be our alpha, our reference angle right there, right? And so we'd have to go 180 plus that reference angle, okay? And then over here, if it landed in the fourth quadrant, this would be our reference angle. So we would have to take 360 degrees minus that reference angle, okay? And this would be the alpha, if it's in the first quadrant, right, the angle of rotation and also the reference angle would be the same thing, okay? All right, and then if it landed here, that'd be 90. If it landed right here, well, let me do over here. If it landed right here, that'd be a 90-degree direction angle. Right here, that'd be 180 degrees. This would be 270 degrees. We wouldn't do 360 because we would just use 0 degrees, okay? All right, because it needs to be the smallest, right? And the smallest for this one would be 0, not 360, okay? All right, guys, hopefully that kind of makes sense for the direction angle. We're going to actually come up with the direction angle for these, okay, on the next page. Okay, all right, that's it, guys. Let's go to the next page. Okay, so we're going to hold off. It's the next one that we're going to do the direction angle and all that. Okay, so here we go. We're just going to do component form, okay? So based on some of the stuff we've learned so far, okay? So find the component form of the vector from the origin to A is 4, 7. So 2, that's the end, right? So this is the head. Okay. And the origin is the point 0, 0, and that's the tail. Okay. So if we're doing that, the diagram for it would be from 0, 0. We start there and we're going to end at 4, 7, right? So we're going to go right 4 and up 7. Okay. So we go more up than we go right. Okay. And so it would look like this, something like that. Okay. And so the vector, okay, would be, so we really don't have a name for this vector, okay, but we would do head minus tail, right? So it'd be 4 minus 0, comma, 7 minus 0. And so this vector would be the vector 4, comma, 7. Okay, and see, it's equivalent to being this point, right? Because because we're starting at the origin. It wouldn't be equivalent to the tail or the head, the coordinates of the head, okay, if we didn't go from the origin. Okay, all right. So like the next example. Okay, so what's the component form of the vector AB? Okay, so we know based on this diagram that this A is the tail now, and the B is the head. Okay, so we can write it this way. Okay, so AB is equivalent to, okay, and it would be 2 minus -5, comma, and then 4 minus 8. Okay, so that would be equivalent to the vector, okay, so 2 plus 5, right? So that'd be 7, comma, 4 minus 8 is -4. Okay, and that's the component form of this vector. Easy enough, right? I mean, this isn't hard. You just have to know the definitions, okay? All right, so let's go to the next example or next page. Okay, so for this one, we want to find the magnitude of the vector and the direction angle, okay? So two things, right? So this is our vector. We know and this is also if it's in component form, so that means it's at 0, 0, or it's in standard form, okay? So what this means is, I'm going to draw a diagram off to the side here. Okay, what this means all right, is that we are going to go to the left negative square root of 3 and up, okay? So it's going to look something like this, okay? You don't have to get, I mean, I'm not looking for it to be perfectly drawn, okay? This is just a sketch to help us, okay? So I know from this that we're going to go left negative square root of 3, and this would be 1, right? And we should actually, and then my arrow should be right here. Okay, so my arrow should be on that end, okay? All right, so what this means is, and we should actually recognize this, right? From trigonometry, right? This is a special right triangle, right? So we could, you don't have to, you could do Pythagorean theorem to find the magnitude of it, okay? So this is 2, okay? So now, because we know it's a special right triangle, we know that this angle, this reference angle right here, what's always opposite 1? It's pi over 6, but really pi over 6 is a 30-degree angle, right? So what's the direction angle? Well, it would be this one, right? Our theta, okay? So our theta would be 180 minus 30 degrees, okay? So theta would equal 180 degrees minus 30 degrees, which would be 150 degrees, okay? So our direction angle is 150 degrees, okay? And the magnitude of this vector, okay, would be 2, okay? Now, I'm going to go through it because it's not always going to be, you're not going to be able to recognize it's not always going to be a special right triangle, okay? Okay, so what we're going to do is we're going to take the absolute value of this vector, the negative square root of 3 comma 1. Okay, so what does that equal to? That's equal to the square root of, and we're going to take negative square root of 3 and we're going to square it, okay? And we're going to add to that, okay, 1 squared. And so this would equal the square, if you square a negative square root of 3, that would just give you 3. And you square 1, okay, you get 1, right? So this would be the square root of 4, which is 2, okay? But again, if you just recognize it, okay, if it's one of these that's a special right triangle, by all means, go for it. You don't have to go through all this, okay? It's just you're not always going to be able to recognize it, okay? All right, so like the next problem, okay? So let me slide up to part B. Okay, so what we now know is that this is corresponding to a vector starting at 0, 0, and the head would end up at -3, -5, okay? So we would have, I'm going to draw my diagram, okay? This is telling me I'm going to have to go left 3 and I'm going to have to go down 5, right? So somewhere like right here. Okay. So this represents the vector -3, -5, right? Okay, and I'm purposely, those are coordinates, not the vector, okay? All right, so let's go with the magnitude first, right? Okay, so let's get the magnitude. So that would be the absolute value of -3 comma -5. That would equal the square root of -3 squared plus -5 squared. That'd be equal to the square root of 9 plus 25, okay? And that'd be the square root of 34, okay? And then that's the magnitude of it, okay? And you could put this into your calculator, okay? And if you square root of 34, you would get about 5.831. Okay, so that's the magnitude of it, okay? Now, I'm going to draw this, okay? And I know from this that this leg is -3 and this vertical leg is -5. Okay, now I need to get this reference angle that's right here, right? And then what I'm going to do is I'm going to take 180 degrees plus whatever this reference angle is, okay? Now this reference angle is an acute angle, okay? And because we know the opposite and the adjacent, we're going to use tan inverse, okay? All right, now, here's where we have to think about this a little bit, okay? We need to make this, because of the way tan inverse works, okay? We need to make sure that we get the right angle here, okay? So we're gonna go back to like math 2, and what we're gonna do is we're gonna pretend this is just a right triangle, okay? And we're not gonna worry about the direction of -3 and -5, okay? So that means we're just gonna ignore this. Now this, we're gonna say the opposite side is 5 and the adjacent side or adjacent leg is 3, okay? So we're gonna do tan, we know that tan alpha is equal to 5/3, okay? That would mean that alpha would have to equal tan inverse of 5/3, okay? Now, because we had to use tan inverse, I want this to be, I want you to make this become positive. I want you to force this to be positive, okay? Because what that does is, remember, that gives us an angle that's in the first quadrant, and all angles in the first quadrant are acute. That's an acute angle, okay? So that's why we kind of ignore the negatives, okay? All right. And so, all right, that if we put this in, okay, we know that that is the exact angle here, okay? So what's my angle of rotation, okay? So that's the direction angle, right? And it's going to be theta, all right, is equal to, and what I'm going to have to do, I'm going to have to go to 180 degrees and add alpha, right? So theta would be 180 degrees plus alpha because of where this ended up at, right? And what's alpha? Alpha is tan inverse of 5/3, right? So theta is equal to 180 degrees plus tan inverse of 5/3. We'd put that in our calculator and we'd get an approximation. Our direction angle would be 239.036 degrees. And I gotta say this, you need to put your calculator in degree mode for this, okay? Put your calculator in degree mode, okay? Because you want it in degrees. Because if you don't have it in degree mode, it's gonna think this is radian. It's gonna give you an angle in radians, okay? All right, so they asked you for the magnitude. What's the magnitude? The magnitude of this vector is 5.831, and the direction angle is this 239.036 degrees, okay? You're always, okay, I'm gonna say something because when you do a vector, this is gonna be the vertical, this is gonna be the horizontal leg, and this is gonna be the vertical leg, right? Okay, so you're always gonna use tan inverse to find the direction angle. Always tan inverse to find the direction angle, okay? And what you wanna do is just ignore the negatives, okay? All right, because that will give you an acute angle, and this reference angle, this alpha, is always an acute angle, okay? Hopefully that makes sense. I wish you guys could ask questions right now and just make sure, or I ask you questions and I know you're getting it or not, okay? All right, let's go to the next one, okay? And I think we're gonna do the reverse. I'm gonna give you the direction angle and the magnitude, and we're gonna come up with the components, okay? So we'll do that next. Okay, for example 3, what we're gonna do is we're gonna find the component form of the vector with a given magnitude that forms the given directional angle with the positive x-axis, okay? So what this means is we have the magnitude is 14 and we know the directional angle is 210 degrees, okay? So if we start, all right, with the positive x-axis and we rotate 210 degrees, right? This would be 180 degrees, and this would be 270. So 210 is somewhere in the third quadrant, right? So we have something that looks like this, okay? And so this would be 210 degrees, okay? And here's my arrow, right? So that's the head of it. Right back here, 0, 0 is the tail. And I know this is 14. So I know the length of this is 14, okay? So how can I find, and what I'm gonna do, let me grab a different color, okay? I know I'm gonna have to find the y component and the x component to this, okay? All right, so you can use the angle and this hypotenuse to come up with the X and the Y coordinate. So the relationship is this: if you take cosine of 210 degrees, well, cosine in this quadrant, right, is going to have to give you a negative value, right? So we're going to pick up the negative value just automatically. Okay, so this is equal to X over 14, okay? And then for the Y, okay, sine, the definition of sine of the angle of rotation is Y over R, right? So Y over 14. So sine of 210 degrees is equal to Y over 14, which you could multiply both sides by 14, and you would have X is equal to 14 cosine of 210 degrees, right? And over here, multiply both sides by 14, and you have Y is equal to 14 sine of 210 degrees, okay? Now, 210 degree angle, right? If we draw the 210 degree angle, we can actually figure that one out because that's a special right triangle. So 210 degrees, okay, 210 degree angle, right, would give you 30 degrees past 180. So your reference angle is 30 degrees. That would make this vertical leg -1. The hypotenuse here would be 2, and this horizontal leg would be negative square root of 3, okay? So from this, we would know that X is equal to 14 times cosine of 210 degrees would be negative square root of 3 over 2. Okay, so our X would be equal to -7 square roots of 3. Okay, over here for the 210 degree angle, we'd have Y is equal to 14 times sine of 210 degrees would be -1 over 2. So Y would be equal to -7, okay? Now, we were able to get the exact value for cosine of 210 degrees and sine of 210 degrees because it was a special right triangle. It's not always going to be, okay? So we're going to have to use right triangle trig to do it then, okay? So we know the component form of this vector would be -7 square roots of 3, comma, -7. It's really trigonometry is what it is, okay? All right. Usually this unit is taught after you do all the trigonometry in like a pre-calc trigonometry class, okay? All right, let's go to part B. Okay, so this time I know my magnitude 7 and my direction angle is 130 degrees, okay? So I'm going to draw a picture of this, okay? So I'm going to rotate 130 degrees. Well, this would be 180 and this would be 90, so 130 would be in the second quadrant. So I'm just going to draw in the second quadrant. That's what's important, okay? So this angle right here is 130 degrees, okay? Now I know this reference angle would have to be 50 degrees. That's not a special right triangle, okay? So I'm not going to be able to use special right triangles to figure it out, okay? So this is 7, right? That's my magnitude. So this is broken up into an X component and a Y component, okay? So how can I get the X component? Well, I know that cosine of 130 degrees has to equal your X coordinate over your radius or hypotenuse, right? So 7. So that would mean X is equal to 7 cosine of 130 degrees, okay? The Y, okay, we could get by taking sine of 130 degrees because sine of 130 degrees is defined as this Y over the R, right? So Y over 7. So Y would have to equal 7 sine of 130 degrees, okay? Now, something I want to point out, this 7 right here, so you could jump straight to these, okay? Because this is the magnitude, right? The 7 is always going to be the magnitude. Okay, and the 130 right here is the direction angle. And you're always going to take the magnitude times cosine of your direction angle to get your X. And to get your Y, you're always going to take the magnitude and multiply it by sine of your direction angle, okay? Because this denominator is always going to be your magnitude, okay? Because it's the hypotenuse, right? And that's the length of the vector, okay? All right, so the exact answer to this would be the vector would be 7 cosine of 130 degrees, comma, 7 sine of 130 degrees. Okay, to get an approximation of that, we could put this in our calculator. Okay, and if we put 7 times cosine of 130 degrees, we would get negative 4.500. Okay, and if we put 7, and you would need to make sure that you're in degree mode. Okay, or you use the degree symbol to put in here. Okay, and then this would be 5.362. And those numbers, okay, you can't tell if these make sense, but you can tell that these make sense because, yeah, to get here, you'd have to go left, right, which is be negative, and you'd have to go up, which is positive, okay? So just kind of I mean, you can't really see if the numbers are right, but you can just tell, okay, by being in this quadrant, I know my x, this is gonna have to be negative, and this one's gonna have to be positive, okay? All right, let's go to the next page. Okay, so this is just going to be some information, okay? You can do vector addition, so you can add these mathematical things, these things called vectors. You can add them, okay? You can find the product of the vector times a scalar. That's actually just going to stretch it, okay? You can find the opposite of the vector. That's like if you're going right, the opposite of that would be going left, okay? So you have to take the negative of it, okay? You can do the difference of two vectors, okay? And the difference of two vectors is really, it's gonna wind up being subtraction, but it's really, you take the first vector and you add the opposite of the second vector, okay? All right, so let's take a look at this. What we do to get this is we just add, hold on a second. Okay, so like this one, if we do the sum or the resultant of the vectors u and v is a brand new vector, okay? So this would equal, okay, a new vector that would be u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2. So we just add the components, okay? All right, how about a product of the scalar k in the vector, okay? So if we take k, some number k times a vector, okay, it would just be k times u sub 1, comma, and then k times u sub 2, all right? If we took the opposite of some vector v, so negative v, right? That would be equal to negative 1 times v. So this would equal negative v sub 1, comma, negative v sub 2, okay? If you, the difference of two vectors, okay, so what we would do with this one is it turns out to be adding the opposite of the vector, right? So this would be the vector u sub 1 comma u sub 2, and then plus the opposite of vector v, right, which would be negative v sub 1 comma negative v sub 2. And what we would get is the vector u sub 1, adding negative v sub 1, right? So it'd be minus v sub 1, comma, u sub 2 minus v sub 2, okay? It kind of makes sense. I mean, they do what you think they would do, okay? All right. All right, so let's do this next problem. Example 4. Okay, so this new vector that we're going to get out of 3u plus 4v, okay? So this is a scalar times u, and it's also a scalar times v, the vector v, and then we're going to add those to each other, okay? So this would be equivalent to, and I'm going to write it like this, 3, and then I got to find out what those are called. These are called something, I don't know off the top of my head what they're called, okay? And then negative 2 comma 4, and then plus 4, 3 comma 5, vector symbols. I don't know what else to call them right now. Okay, so that would mean that we're going to add the vector. So this is a scalar times a vector, so that would be 3 times negative 2, which would be negative 6, comma, 3 times 4, which is 12, okay, plus this new vector, which would be 12, comma, 20, right? And we got to put the symbol for vectors, okay? And now what does this say to do? Well, now I got to add these, right? So this new vector that we get out of this would be negative 6 plus 12, which would be 6, comma, 12 and 20, and that'd be 32. Okay? All right, so then this next one, B, we're in essence defining the difference between two vectors, okay? So this would be u. We can't really do it this way, okay, because there's no operation like this, okay? So it'd be u plus -1 v. Okay, so that would be the vector -2 comma 4. Notice they say vector, and it's not the point. Okay, so the vector -2 comma 4 plus, and then it'd be -1 times, if we really wrote this out perfectly, okay, 3 comma 5. Okay, so this would be equivalent to -2 comma 4 vector, and then this one would be plus, and this vector would be -3 comma -5. Okay, and then this would equal -5 when we add them, -5 and comma -1, and that'd be the new vector. Okay, so this is how you combine vectors. Okay, all right, so what does this one mean? Well, this one means, remember, the absolute value means magnitude, right? So this is equivalent to 3 times the vector -2 comma 4, and that would equal the absolute value of the vector -6 comma 12. Okay, and now we have this vector to deal with, right? And so this would equal the square root of -6 squared plus 12 squared. Extend my square root. So this would equal the square root of 36 plus 144. Okay, and that would equal the square root of 180. Okay, and then you could put that in your calculator. All right, and you could get an approximation for this. Okay, because the others we got were exact. Okay, so we'll put this in our calculator, and when you put it in your calculator, you get 13.416. Okay, so that's going to give you, the magnitude is going to be a scalar amount, right? Okay, it's not a vector. All right, because it's the size of it. Okay. All right, guys, let's do one more problem. Okay, so for this last example, this is kind of a practical example, okay? A Boeing 727 airplane flying 10 degrees north of east at 575 miles per hour, okay? I'm gonna call that one U. Okay, so it's a magnitude and a direction, right? This is a vector, okay? So I'm gonna draw this in. Okay, and there's forces acting on this. Okay, so we'll talk about that in just a minute. This is something you did in physics. Okay, all right. So this would be north. This is south, and never ever eat soggy waffles, right? Or never eat soggy waffles, right? So this is west, and this would be east, right? Okay, so this would be due east, right? And so it's saying a Boeing 727 airplane flying 10 degrees north of east. Okay, so it's not going east, it's going 10 degrees north of this, right? So it's kind of coming up this way. Okay, so I'm going to draw that. It's coming up this way. Okay, and I know that this vector right here is 575 miles per hour. Okay, and I also know that this direction angle is 10 degrees. Okay, and it encounters a 70 mile per hour tailwind acting in the direction of 20 degrees east of north. Okay, 20 degrees east of north, of true north, right? So north, and it's 20 degrees east of that. So we're going to rotate this way, right? And so this vector, I'm going to do a different color. Okay, so for this vector, it's like this. It's going to be much shorter than this one, right? Because this one's 575 and this one is 70. Now it does not have to be drawn to scale or anything. Okay, but this one is 70, right? Not 70 degrees. It's just 70 miles per hour, and it's acting on this. Okay, and it's 20 degrees east of north. So north, and it's going to rotate 20 degrees east. So this angle right here is 20 degrees. Okay, and the airplane holds its compass heading due east, but because of the wind acquires a new ground speed and direction. So we want to know what the new ground speed is. These are the grounds. This is the speed right now of the actual plane. Okay. All right. Okay. So what happens is, I didn't mean to do that in green. I was going to do something else in green. Okay. So that's 20 degrees. All right. What we can do is, this is how you add, this is actually how you add vectors, okay? So we're gonna take this one and it's head to tail, okay? So you're gonna slide this one and it's gonna be in the same direction, but from this, okay? Because this one, all right, is gonna be the same as this one, okay? And this one is, let's call, well, these are the same vectors, okay? So if the blue one's U, let's call that one U, okay? U would be 575. That would be the magnitude, and it's 10 degrees. Okay, now if this angle's 20 degrees, then this angle right here, the direction angle would be 70 degrees, right? So V would be 70, all right, miles per hour. I should put miles per hour. Miles per hour. And it would be 70 degrees. Because it's 20 degrees from north, north is 90 degrees, so that'd be 70 degrees, okay? All right, so if we find this vector, we're going to have it all, okay? And this vector represents the addition of these two vectors, okay? And this would be, if this one's V and this one's U, this green one is U plus V, okay? All right, so from what we learned just a minute ago, right? Okay, U is equal to the magnitude, which is 575, cosine of the direction angle, right? 10 degrees. So this would be 575 cosine of 10 degrees. That would be the x component of U. What's the y component of U? Well, it'd be 575 sine of 10 degrees, okay? And that would be the x and y component, okay, of them, all right? Now, what's V? Vector V would be 70 cosine of 70 degrees. So 70 cosine of 70 degrees. And the y would be 70 sine of 70 degrees. Okay? All right. So, okay, with that said, what is this U plus V? Okay, so that's going to give me the component form of this vector, okay? So basically what happens is the wind, right? The wind is going to push the plane in this direction, right? Okay, and it's going to wind up over here, okay? Because the wind is pushing the plane in this direction, right? Okay? Okay, and this is breaking up it into an x component and a y component, and this one into an x component and a y component, okay? So when we go to add them, we're going to get the resultant vectors, okay? So U plus V would equal, okay? And it would just be this component plus this one, right? So 575 cosine of 10 degrees plus 70 cosine of 70 degrees, comma, and then 575 sine of 10 degrees plus 70 sine of 70 degrees. All right, and then we could put that in our calculator. Okay, and this vector, the approximation, okay, and we'd want to store it, okay, is 590.206. Okay, so we want to put this in our calculator, and we're going to call that one A, all right? And then comma, so we're going to let A equal 590.206. Okay. And then if you put this one in your calculator, okay, 575 sine 10 degrees plus 70 sine 70 degrees, you get 165.626. Now it has more decimals than that, but that's what we're going to use, okay? And we're also going to let B, I need to close my vector, okay? And my B is 165.626, right? Okay, so we want to find the magnitude and the direction, okay? So, okay, with that said, okay, the magnitude would equal, okay, it would be the absolute value of the vector 590.206, comma, 165.626, right? But we're calling this A and B, right? So this is equivalent to the absolute value of the vector A, comma, B. And we store that like alpha A and alpha B, okay? All right, so then the next thing we need to do is to find this, we would take the square root of A squared plus B squared, okay? And if we put that into our calculator, we get an approximation of 613.005 miles per hour. Now it had a tailwind, right? And what a tailwind means is it's pushing it. So the plane was going 575 miles per hour, but the plane was, or the wind was pushing it. So actually on the ground, it looked like it was going 613.005 miles per hour. Okay. Now what's the new direction? Okay. It's going to be, and it's going to be a little bit more than 10 degrees now, right? Okay. But it's going to be less than the 70 degrees for sure. Okay. Now it's in the first quadrant, right? And remember, we did this. Okay. So tan, I'm going to do direction angle. Let's do that next. Okay, so I know that tan of my reference angle alpha, and in this case, alpha, because it's in the first quadrant, alpha and theta are going to be the same angle, okay? So tan of alpha is equal to my opposite, right? So for this one, it'd be the B, right? This is my B over my A, because this is my vertical leg, right? So it'd be B over A, which would mean alpha, which is also going to be theta, is going to be tan inverse of B over A. The B and A value that I stored up here, okay? Okay, so we're in the first quadrant, right? So alpha in that first quadrant, the alpha and the theta are going to be the same, okay? So since alpha and we're in the first quadrant, this is also going to be theta. So theta is equal to tan inverse of the B over the A, okay? And what you wind up getting is an angle that's about, and you need to be in degree mode, okay? 15.675 degrees, okay? So now what does that mean? That's from the positive x-axis, right? So that's north of east, okay? Because they asked you, what's the new ground speed and direction, okay? And what are they, okay? So the new ground speed from this tailwind is 613.005 miles per hour, and it's flying. Let me slide it up just a little bit. Okay, and it's flying 15.675 degrees north of east. Okay, so that's the new ground speed and the heading or direction, okay? All right. And that's your baptism into baptism into vectors, okay? Tomorrow we're going to do calculus with this, like we're going to do derivatives of vectors and all that kind of stuff. And it's very similar to parametrics, okay? So don't get nervous about it at all, okay? Plus, you're not going to take a test on this, all right? You're just expected to know this, all right? for the next math class. All right. All right. So that's it for today. Okay. Let me get the assignment sheet and we will finish this up. Okay. So what I want you to do today, okay, well, not necessarily today, but for this assignment, for what you learned today, I want you to do page 552 and I want you to do 1 through 25 odd. Okay. And it's just vector operations, adding, scalar multiplication, stuff like that. And then I think there might be a couple planar motions, like that, like what we did just now. Okay. All right, guys, take care. I will see you mañana.